Hi everyone! In this video we are going to go over another reaction that takes place at the alpha position, and that's called the Aldol addition reaction. Now aldol is referring to a molecule that has an aldehyde functional group and an alcohol functional group. So we've got ALDOL for aldol. So for example, let's say we're reacting two aldehydes together, and we'll use the same aldehyde. So this one's called acetaldehyde. We're going to also add some sodium hydroxide and water, and this will give us that aldol that we talked about. Now, this is also called a beta hydroxyaldehyde. And that's because if we use that Greek symbol method to label our carbons, the first carbon next to the carbonyl group is labeled alpha, the next one is beta, and we have a hydroxy group on the beta carbon, so it's beta hydroxyaldehyde. Also, the bond in between the alpha and beta carbon is the bond that formed between the two aldehydes. So that is our new bond. Now, aldehydes work better for this reaction because they are more reactive. So let's just make a note of that. And this is compared to ketones. We will talk about ketones later on, but for now we're just going to use aldehydes because they do work better for this type of reaction. So let's look at the mechanism for this reaction. So we're going to start with our aldehyde, and we also have hydroxide ions from the sodium hydroxide that was added. And again, all of this is going to take place at that alpha position. So let's draw some alpha protons. And the hydroxide ion is going to grab onto one of those alpha protons. That will leave electrons behind and move electrons up to oxygen. Now, what we end up forming is an enolate. Now, the aldehyde is actually going to be favored over the enolate. So if we draw equilibrium arrows, we're going to draw a really large arrow going towards the aldehyde and a really small arrow going towards the enolate. However, as we start forming product, we can remove it to favor the products. All right, now let's react that enolate with our other acetaldehyde molecule. So that negative carbon on the enolate can act as a nucleophile and attack the aldehyde carbon, and that's going to move electrons up to oxygen. So now we've connected our two molecules. So on one side, we still have our aldehyde, and then we formed a new bond to the other aldehyde, which has now become almost an alcohol. We're not quite there yet. We also need to use water. And then that will protonate the negative oxygen. Okay, and then there's still that hydrogen there on the beta carbon. I just didn't show it in the final product. Okay, so what's also really cool is that we can reverse this reaction. So if we start with our beta hydroxyaldehyde, we can go back to our original aldehyde. So the red arrows that I was using for the forward reaction, that shows the mechanism for the aldol addition reaction. But we could just as easily show the reverse. So I'm going to use a different color for the reverse reaction. Let's use blue. So in the reverse reaction, we're going to have hydroxy ions floating around, and that came from our water molecule there. But that hydroxy or hydroxide ion can deprotonate the alcohol group, and then we end up with our negative oxygen in the next step. That can reform its double bond, which is going to kick out the enolate as a leaving group. So that takes us back up to the second step. And let's see, we will have some water present in solution at that point. So then the enolate will actually, oops, I drew that wrong. Let's see, the enolate will actually grab a proton from a water molecule and will end up reforming our aldehyde in the original starting materials. So the blue arrows are showing what's called the retro-aldol reaction. So it's just the reverse of the aldol addition reaction. So let's do a practice problem for these aldol addition reactions. So I'm going to give you a starting material. And you can assume you have 2 of the starting material. And then we're going to, again, add sodium hydroxide and water. And then I would like you to pause the video and try to figure out what the product is for this aldol addition reaction. And then when you're done, we'll go over it together. All right, so I think what we'll do is try to use different colors for each aldehyde that we're using. Now, in the first step, we know that one of the alpha protons is going to leave with our hydroxide ion to form water. And that will form, oops, there we go, our enolate. And then let's draw our other aldehyde, which is just the same as the one we started with. Let's draw that in orange. Okay, so now we know that in the next step, the enolate is going to act as a nucleophile and attack the carbonyl carbon on the aldehyde. That's going to move electrons up to oxygen. And then we're going to form a bond between these two. Let's see. So I will draw the bond in orange, but I'll also highlight it in a bit so that we know it's a new bond. So the highlighted bond is the new bond that formed between the enolate and the aldehyde. And then I tried to use the different colors to show where all these pieces are coming from. So our enolate is now giving us the aldehyde in our product. The aldehyde in orange is now going to give us our alcohol group. But first we have to protonate that negative oxygen. So we'll just use water to do that. All right, so let's draw the final product. Let's see if I can fit it onto this very small space. I kind of did it. All right. Here, I'll make my hydrogen on the aldehyde a little smaller so that it doesn't quite run into that ring there. Okay. Now, in these reactions, sometimes you do need to count your carbons just to keep track. So, for instance, maybe on the aldehyde, we could have counted, okay, I have 1, 2 carbons there. So now in the product, oh, whoops. This should be a hydrogen here. I apologize. That's a mistake on my part. That's not a methyl group. But in our product, we can then count, okay, we have carbon 1, carbon 2, and on carbon 2, we have this phenyl group. On carbon 1, we have a hydrogen. Okay, that checks out. And then we could even do the same in our final product, just to make sure that we have all of our carbons. All right, let's do a slightly harder problem. What if we're given the product and we have to figure out the starting material? And remember, the starting material will just be multiplied by 2 since we're reacting 2 of the same aldehyde together. So our product for this one is going to look like the following. So again, we've got our aldehyde and our alcohol. And I'll give you a hint. Find the alpha and beta carbons because that will help you figure out what your original aldehyde was. So pause the video, see if you can figure out the original aldehyde, and when you unpause, we'll go over it together. Okay, so let's find the alpha and beta carbons in our product. So we'll start at the carbonyl carbon and move 1 carbon over. That is our alpha carbon. And then we're going to move 1 more carbon down to the alcohol carbon there, or the carbon connected to the alcohol, and that is the beta carbon. So what we can do is say, okay, that is our new bond that formed in the reaction. And let's just cut that in half. So let's use a retrosynthetic arrow here. So it looks like then we had our enolate on the top, And then the other half was our aldehyde. Okay. Now what that tells us is we just started with 2 of that aldehyde. All right, and that kind of looks like the top half of our molecule at the end. So if you can kind of visualize where the new bond formed, so if you can find the alpha and beta carbons on your aldol product, that can help you figure out what the starting material was. Okay, now let's talk about another reaction that's very similar. In fact, it's mostly just an extension of the aldol addition reaction, and that's called aldol condensation. So in this reaction, again, we start with our aldehydes and we add sodium hydroxide as well as water. And so far we've seen that will form this beta hydroxy aldehyde. But additionally, if we add heat, what we end up forming is the following. So we end up almost doing an elimination reaction between the alpha carbon and the beta carbon, and we form a double bond. And this product is called an alpha beta unsaturated aldehyde. So let's look at the mechanism for this aldol condensation reaction. So the beginning of this mechanism will look pretty similar. We're starting with hydroxide, and the hydroxide ion is going to take one of the alpha protons, which will leave electrons behind, move electrons up to oxygen. And we end up forming that enolate. And that's just one of our resonance structures. So we could actually even skip the arrow showing the movement of electrons up to oxygen and just show that the shared electrons from carbon and hydrogen are just going to carbon there. And now we're going to react our enolate with our aldehyde, just like we saw before. Okay, so this is where we've gotten to previously. Just going to protonate that oxygen to create our alcohol. Okay, so what happens now if we add heat? So we do have hydroxide left over from water in the previous step, and we're going to add heat. So the hydroxide ion is now going to take a proton from our alpha carbon on the beta hydroxyaldehyde. And this is going to leave behind a double bond, and then our OH group is going to leave. Now, since we are forming a double bond between the alpha and beta positions, oops, I didn't mean to zoom in there. We could form the trans alkene or the cis alkene. So we have 2 options here. or two possible products, I should say. Oh, I just redrew the transalkene. There we go. That's the cisalkene. Okay, so looking at the transalkene and the cisalkene, do you remember which one is more stable? The transalkene is more stable. Why is the transalkene more stable? Do you remember? So remember, it has to do with electron groups and Vesper theory. So electron groups want to be as far apart as possible, right? So in the trans position, those electron groups are far apart. So that's going to be more stable. And the trans product is the major product. The cis product is therefore the minor product. Okay. So let's just summarize everything that we've talked about so far. So we just saw that aldol condensation is favored at higher temperatures. We also, therefore, can say that aldol addition reactions, so the first reaction we covered here, is favored at moderate temperatures. All right. Now, the condensation reaction is also going to increase in terms of entropy because two products will be formed. But we're also going to create some conjugation. Now, both entropy and conjugation are favored at high temperature. So let's go back. Let's actually look at our aldol addition reaction. So notice that the entropy decreases for this reaction because we're taking two starting materials. So we have 2 moles of starting material, and we're turning that into 1 mole of product. We also don't have any conjugation in that product there. But then if we look at our aldol condensation reaction, oh, here we go. We're taking our starting material, the aldehyde, and we're turning it into 2 products, a trans and cis product. So entropy is increasing, but additionally, notice that we have 2 double bonds that are separated by a single bond, which increases conjugation. And conjugation is pretty stabilizing. So these are all just things to keep in mind as you're thinking about reactions. How stable are they? When are they favored? Are they favored at low temperature, at high temperature, etc.? All right, so in the next video, we're going to discuss another version of the aldol reaction called the crossed aldol reaction. So what happens if we try to combine two different aldehydes instead of two of the same aldehyde. So I will see you then.